See what that says. Welcome to the Computer Security Seminar. Today's speaker is Casey DiCio from Sandia National Labs. He will talk on modeling DNS security, misconfiguration, availability, and visualization. Casey.
Thank you. Well, it's good to be here. I'm going to talk about some of our experiences. A lot of this comes from operational experience with dealing with DNS and deployment of DNS security, or DNSSEC. So I'll explain a little bit of background behind that and take it from there. And if you do have questions along the way, feel free to ask them as they come up, and I'll be happy to answer some questions. So first of all, this is kind of the motivation slide. DNS is behind just about everything that we do on the network. Okay, it provides the critical mapping between internet names, such as www.example.com, and internet resources, most commonly IP addresses. But is very important, as if you, I'm sure you're all somewhat aware of that. Okay, but the problem is that DNS needs to be both available and it needs to be trustworthy or accurate. Okay, security, when DNS was originally designed, there wasn't security involved in it. Security was added later as a retrofit, and that's what we know as DNSSEC. DNSSEC is the most commonly most common form of DNS security out there. Okay, and it increases the complexity significantly of DNS, and I'll show you some examples of that in a little bit. You used to be able to just set up a DNS setting and it would just work for a while, and very low maintenance. Okay, troubleshooting DNS security is also very difficult, and that's some of the motivation behind doing this. So here are some of the examples of failures that we've seen. Medicare.gov, NASA.gov, .be, which is a top-level domain. Okay, so some of the objectives in the talk today to look at DNS and DNSSEC, establish kind of a model and some metrics for actually measuring availability with DNSSEC in DNSSEC deployments, and then take a look at some of the reasoning behind why some of these misconfigurations happen that cause availability issues. And then finally introduce some of the techniques to mitigate this misconfiguration so that you can still go to www.google.com even if there's something wrong with it down the road. Okay, so we're going to begin by talking a little bit about DNS and DNSSEC background. Then I'll outline again some of the the types of DNSSEC misconfiguration. Then I'll talk a little bit about DNS complexity and contributing factors to misconfiguration. Then I'll discuss some of the work talk about mitigating misconfiguration so you can still work in the midst of misconfiguration. And then talk about some work we've done in DNSSEC visualization, and then summarize at the end. Okay, so just a little bit of review, and I'll just spend a little bit of time on these slides. But DNS namespace is organized hierarchically. Okay, so you delegate out your management so that you start with the root at the top, then you have your COM and net, for example. And a zone is what we refer to as an autonomously managed portion of the DNS namespace, like bar.com in this particular example. Okay, so that's the way the namespace is organized. Now, the way that name resolution works is that you have what we refer to as a resolver. In this case, two different resolvers, two different roles of resolvers. There's the sub-resolver, which queries a recursive resolver, and the recursive resolver is the one that's going to do all the work. Okay, the stub resolver is the one that you configure in your client, your computer, to go out and ask the question. It is the computer that goes out and asks the question, basically, and the recursive resolver is doing all the work. It starts at the top and basically follows referrals downwards in the hierarchy until it gets to a server that's authoritative for the zone in question, in this case, www.bar.com. Now, the problem is, where a lot of the attacks come from, is that since DNS is UDP based, the attacker has to do you're not actually talking over a connection. So all the attacker has to do is be the first one to respond to a particular DNS request. Okay, and in this particular example, if the attacker can get the respond with an answer before the authoritative server can respond, then that's stuck in cache, and it could be for an arbitrary amount of time. It could be anywhere from minutes to a week or something like that. Okay, so so DNSSEC was introduced, and DNSSEC is again only one of several implementations of DNS security, but it's the one that industry has gone with and the most standardized. So that's the one I'll talk about today because it's currently under deployment. Okay, so the way DNSSEC works is you're introducing a private key, public key system, and the private keys are signing the data. The public keys and signatures are used to verify the data. So in our particular example here on the slide, you have now www.bar.com is the question we're asking. The server is going to respond with the answer, but it's also attaching a signature. It's an RRSIG is the resource record type that goes along with it. And then it also has to now get the public key, which is embedded in the zone data. So you actually query your server not only for the answer and its signature, but also for the public key, so now you can verify it. And if everything checks out, it does the validation succeeds, then it sends a response back to the stub resolver. You're pictured as your computer here in the slide, with what's called the authenticated data bit set, so that it knows that the server has validated that. Okay, and that is DNSSEC in a nutshell. Okay, now what happens is the way that you do this, you have to have some notion of trust before you can use DNSSEC. The resolver has to, just like in your web browser, you have to have some root authority. That's what a resolver has to be pre-configured with a trust anchor, what we refer to as a trust anchor as well. And that's typically done at the root zone, the highest level, and that way you only have to maintain a single trust anchor. And the trust anchor refers to the key, so you know that the key is valid, and then you form a chain using the example here from bar.com. Your zone data is signed with the DNS key, so that's what the arrow represents. And then use this, what's called a delegation signer or a DS record in the parent zone, which maps to the DNS key. Okay, and then so you have, and it maps with a hash of the DNS key. And so by signing that with the rest of the zone data, you're able to verify the parent basically affirms that yes, this is the DNS key, a hash of the DNS key of the child, so you can form what's called a chain of trust from bottom to top. So a resolver now, with a single trust anchor, can verify anything in DNS with this chain of trust. Okay, now there is some notion of backwards compatibility with DNSSEC, meaning if Purdue.edu is not signed, then has not signed, it's okay if edu is signed, but Purdue.edu is signed. Okay, and otherwise this would break a lot of things if this weren't the case. Okay, beginning with the root, which was signed last July. Otherwise everything below it would be broken right now. So the way this works is you have, if a child zone below you is not signed, then you have what's called an NSEC record that basically shows that no DS record exists. It's a proof provided by the authoritative server that a DS record does not exist. And that is necessary so that a validating resolver can show that it shouldn't expect any signatures to validate. Okay. So there are some special things, as I mentioned previously, with regard to maintenance that are special to DNSSEC that you didn't have to worry about with regular DNS. First of all, the signatures that you get that are the RRSIGs, they expire over time, so you can't use them as a replay attack years in the future. So they have a time period when an inception date and an expiration date, and that is your lifetime of the signature. So it can't be used before the inception date, can't be used after the expiration date. Typically what that means is that you need to re-sign your zones periodically. And if you don't, then they'll expire. And I'll show you some great examples of that in a little bit. Also, they recommend that your DNS keys are rolled, similar to how you might change your keys out for different applications. SSH, your session key, periodically rolls, for example. Okay, DNS key, the same thing. So that to avoid prolonged exposure, they recommend that you roll them. But that's kind of a headache because, as I showed you earlier with the chain of trust, I'll back up just a couple slides, you have this DS mapping with your parent, meaning that the DNS key has to be has to be a hash. The DS record has to be a hash for a valid DNS key, otherwise you have an invalid mapping into your zone. So when you change this key, you have to coordinate with your parent. Okay, some complications in there. And then the other aspect is that if you have a number of different servers serving authoritative data for a particular zone, which is fairly common, then you'll want to make sure that all those servers are serving consistent data. That means they're all serving signatures appropriately. They're all serving the same data. We've had some cases where some are serving expired signatures, some are serving valid signatures, for example. Some aren't serving signatures at all. I'll show you some interesting cases a little bit later on. Okay, so next talk about classes of DNSSEC misconfigurations. So first of all, to better understand our model for measuring availability in a DNSSEC deployment, we've classified things into 3 different classifications. And these are fairly arbitrary, but to understand this, that's why we've done this. So what we call zone class misconfigurations, or we have something specific to the zone, meaning you are either missing your signatures or they're expired or bogus, meaning they don't validate against the data that you have. Or if your DNS keys are missing, you get the same type of result. Okay? Delegation class misconfigurations would be if you, the case where I mentioned where your DS records, there are DS records in the parent, but they don't map to any DNS key in the child. There's a problem, you have a broken delegation. Okay, and you can't follow the chain of trust down. And then there's also, if you have your trust anchor that's maintained at the resolver, the one that's actually doing all the work, if something changes with the DNS key at the on the authoritative server that corresponds to that trust anchor, and your trust anchor doesn't change accordingly, then you'll have problems as well. Okay, so those are 3 different classes. And in this presentation, we'll just focus on the 2, the zone class and delegation class. So now here's one of the issues, is that it's not a cut and dry that you're either going to get a failure or a success when it comes to DNSSEC validation. The reality is that partially because DNSSEC is so new in terms of implementation and deployment, is that sometimes you're getting a mixed bag where there's a possibility of failure because some of your servers aren't serving the same data. They're again, inconsistent responses. And so basically what this equation looks at, it's the probability of bogus validation, meaning the probability that you'll get bad data from hitting these servers. And this is based, of course, on the assumption that there's equal probability that you'll query any of these servers. Okay, so if you take the number of bogus servers and divide that by the number of responsive servers, that's what we call failure potential for a particular zone. So in this case, the failure potential would be 1/2 because you have one serving valid data, one serving bogus data. The non-responsive one we toss out because a resolver knows to just try again if it gets that one. Okay, now when you take this and you actually have different levels in your hierarchy, this could happen, this problem with hitting a server that's serving bogus data could happen anywhere in your hierarchy. And since you have to complete this chain of trust, you now have to multiply this together such that you get this equation, which basically takes all the probabilities and it's multiplies them together independently, so you get 1 minus the probability that you have no problems in any of your zones. Okay, so we did some analysis over a period of about 5 months, and we looked at about 2,200 production signed zones. Now there are more zones signed than this, by the way. This was a sample of data that we did, and excuse me. So over this 5-month period, what we did was we polled each zone about 6 times daily, looking at the zone and specifically looking at the SOA record for the zone. the start of authority record, and then tracing that up to a trust anchor. Now, prior to, we just put it up to a known trust anchor. And then, so here are some of the results. And so one other thing to mention here is what we classified as a failure event was when for 2 or more consecutive polling periods, we consider that a single failure event. So if something happened, if a signature was expired the first time we hit it, we didn't count it until we saw it a second time, and that was mostly to give us kind of the benefit of the doubt. So any of the events that you see here are if it happened for more than a 4-hour period, which is makes the results all the more interesting, I suppose. Okay, so what we found was total instances of non-zero failure potential. There were 2,634. Okay, now 76% of these were actually instances of what I call possible failure, where again you had some chance between 0 and 1, some fraction possibility. And then the instances of certain failure where it didn't matter which server you queried, you were going to get a bogus failure. A bogus result. Then that was the remaining 24% of those instances that we saw. Okay, so here's kind of a breakdown of the different things that we saw during the survey, which I also find interesting. You might suspect that that the expired signatures was the largest contributor, and it was in terms of certain failure. Okay, so go back to the certain failure versus possible failure. This graph shows the two side by side for each type of failure, and this is the raw number of failures. So on the far left, the lighter colored yellowish bar shows about 400 instances of expired signatures. Okay, and that were across the board, meaning didn't matter which server you're hitting, you'd get an expired signature for that particular zone. Okay, and then you had a smaller percentage that were around 100, where part of your servers were serving expired signatures, so they didn't quite get everything in sync. Okay, and that was the largest contributor because it's easy. You just don't resign your zone and things go stale, your signatures go stale. That one's why we see the largest contributor. There were also, interestingly, if you look at the second one, the missing RR SIGs, you see that there's a large contingency of those, nearly 750 instances of those, for partial failure. And that's because what we found is as people started deploying DNSSEC, they would sign their zones on a server that supported DNSSEC, but they would have a slave server, a secondary, that was also serving their zone, but didn't support DNSSEC. And so it didn't know that it was supposed to return signatures along with it. And so that was an interesting case that we saw out there. In other cases, which I don't have recorded down here, you'd see where some of these servers would not serve NSEC records, which is a problem because then you can't, the whole backwards compatibility thing doesn't work anymore now. If you have an unsigned zone below it, but you can't prove that it's unsigned, then you have a problem with backwards compatibility. Okay, so some interesting results there. So if we look at what the failure potential looked like on here, this is the breakdown again. What was the probability that you would get some kind of failure if your resolver was going to all these different servers and querying them for things that you would get a bogus result. Okay, and if you look at the average, which is the one on top here, these colors look fairly similar, then what we found was the good news is that there were about 83% that maintained a zero failure potential over this 5-month period. The bad news is that the other 17 or so percent ran into this. They averaged non-zero, meaning they had some kind of type of incident that made them subject to some kind of failure on the validation end. Now, if you look over on the far right, in the upper right-hand corner, what you'll see is there was about 2%. There were about 2% of these zones that we did that never left the ground. During the entire time that we pulled them, they had some type of problem that they were completely unvalidatable. And so some of that might just be an awareness issue that people don't realize that when we turn on DNSSEC that people are actually validating and have problems with this. So, hey, the bottom line in this is the maximum, and I simply show this to show how many people had a failure potential of 1 versus some partial, meaning things went completely wrong and there was no chance of validating. And so it looks like there were about 17 or 18% there that had some type of event during this polling period that made them completely unvalidatable, which is actually, if you think about it, that's almost 1 in 5. So pretty big contingency based on this sample size that we had. Okay, so the next thing we wanted to do is look at this. Okay, people are deploying DNSSEC. They're having some problems. Maybe it's just a new technology, but what are some of the problems that are contributing to these misconfigurations that we're seeing? So we want to take this analysis a little bit further, and so what we came up with is a complexity analysis. And if you think about the way that we looked at failure potential, there are actually 2 dimensions. Okay, so the one dimension we were looking at that contributes is hierarchical. So the longer your chain, the more problems, or the more places where problems can occur. So you've got the root zone, the top level domain, the second level domain, and so on. And we saw chains as long as 4 or 5 long, DNSSEC signed, and maybe longer, but those were some of the ones that we saw in production. Okay, and then administrative complexity has to do with I run my zone example.com, and I have, we'll use an example that's closer to home, purdue.edu, and you want to share with servers with illinois.edu because they're good friends. Maybe Indiana, I don't know. Okay, so you guys are hosting each other's data because it's cheap. That way you get high availability, right? You host their DNS services on your DNS servers. They host your DNS services. Did I say that right? You host each other's DNS services, okay, on each other's servers, except maybe after a basketball game or something like that. Okay, but the point is, if you're sharing DNS services across different organizations, what happens is there are changes made unilaterally that may affect things. And in regular DNS, you may not see them as much. But when you start applying DNSSEC, you may have things that, for example, your server maybe doesn't download the new zone version because of a firewall change that you just don't detect. And now you have, it was a change made unilaterally on the other organization side. So your signatures expire in that, coming from that particular authoritative server. Or it could be that the server in the other organization doesn't support DNSSEC at all, and you're just unaware of what server versions that they're running. Anyway, we wanted to look at this correlation and see how it actually came about. Okay, so looking at the hierarchical aspect, we asked ourselves, okay, if you could reduce your namespace hierarchically, then how much could it be reduced and still preserve what your names actually look like? So for example, let's say you have these 4 in the slides here. You have a depth of 4 here, okay? Your root, com, bar.com, and sub.bar.com. Well, what you could do is, if you're really running both the bar.com and sub.bar.com zones, and you just have these 2 different zones for administrative reasons or something like that, could you feasibly roll those into one, and so that www.sub.bar.com was actually in the bar.com zone, okay, for maintenance reasons. What that does then, it eliminates another place where things can go wrong, and so in this particular case, the reduction is 0.25. Okay, and I gave a presentation that talked about this a while ago, and then I noticed that a group one of my colleagues in Europe, I saw some anomalies on his zone. They weren't bad, they were just some anomalies that I saw, and I emailed him about it, and he wrote back and said, yeah, we're flattening or rolling one of our zones into another one. And I said, you must have seen my presentation. He said, yeah, I did. So anyway, kind of interesting. So administrative complexity is basically answers the question, how diverse is the set of organizations that are administering a particular zone? Okay, so go back to the example where you have Illinois, Indiana, and Purdue all hosting Purdue.edu's services, okay? So the way that we do this, we wanted to have some idea of what the distribution looked like with a single number so we could do it for comparison. And the way we did that was by basically using random sampling with replacement. So if you were to put all these organizations in a bag, and pull out, or excuse me, all your servers in a bag and pull out two marbles, two of your servers, I guess, in this case, with replacement, then what's the probability that you get two distinct organizations? And so that's all this does. In this particular case, it's 0.5 is the answer. So if we look at administrator complexity mapped with the types of errors they were getting, this is actually kind of what we expected to see with this. But if you look at the bar on the very top, the line on the top, that represents zones where we saw no non-zero failure potential. Okay, and that one's fairly high. What that means is that there were 80% of zones with no events had a 0 administrative complexity. Meaning all the administration was self-contained. Okay, and then there was a slightly lower number with 0 administrative complexity for those that had a certain failure, meaning everything went wrong. But the one we expected most was down below, the bottom line way down there, which that line represents events that caused possible failure, where you were again between 0 and 1 somewhere, some fraction, and this accounted for, let's say, 40% of these zones that experienced this possible failure had a non-zero, or excuse me, only 40% had 0 administrative complexity. The other 60% had some non-zero number, okay, greater than 0 administrative complexity. So what we're trying to show here is that that a lot of our events could be traced back to these, at least possible failure could be traced back to the fact that there's different organizations administering it, and you just have to be careful when you do that. It's not that you can't, but when deploying DNSSEC, different people have different capabilities on their servers and may make changes and configuration changes, etc. Okay, so the next thing we asked is, okay, we've looked at this a little bit in terms of complexity, but what can we do in terms of mitigating misconfiguration? Okay, you're a large ISP like Comcast or somebody a large ISP, and you turn on DNSSEC validation on your resolvers. Okay, what happens now if one of the top level domains has an expired signature, which you'll see in a couple minutes? Okay, of course you want the security aspect. You don't want to go around that. But how do you mitigate misconfiguration? Because you don't want everyone calling you up your help desk at the same time saying nothing's working. You don't have a good answer for them. Okay, so of course the best thing to do is to follow the RFC guidelines, which tell the zone administrators how to do key rollover procedures properly, how to do trust anchor rollover procedures properly. Okay. There's also this, what I call validation diligence, and that means that simply if a validating resolver wants to get an answer, but it gets a bogus response from somebody, it'll try again the other authoritative servers, if it can. If it can access the other authoritative servers and it gets a bad signature or an expired signature, it'll keep trying. Now, obviously, that'll only help if there is a valid signature on one of the other ones, but that's what I call validation diligence. So the technique that we proposed on top of this is something we call soft anchoring. Okay, and the idea is it uses pre-existing authentication, so you're not going around the authentication chain, but you're using pre-existing authentication chain to build what we call soft anchors in addition to the hard anchors that you already have. Okay, so and the rationale behind this is that you have DNS keys that typically don't change, and so since they don't change very often, you can hold on to those for a little bit longer and kind of renew them once you've authenticated them at the lower levels. So in our example here on the slide, we have bar.com is the zone that we're looking at, and when we first authenticate, when we are looking at a name, have resolved a name in bar.com, then we need to authenticate down the chain of trust here, the DNS key for bar.com, and then once we get that key is authentic. Okay, what we're going to do is store that aside in the resolver as what we call a soft anchor. Okay, and then if there's some kind of break, like in this case, if now the DS record doesn't map appropriately like it should, to a DNS key in the child zone, but we've maintained the soft anchor, and we know the soft anchor is good, so we can try that. We still have a path into validating the child DNS key and therefore the data below there. So if we're using the soft anchor approach, this still works, assuming that we've pre-authenticated it, okay, using the chain initially. And so what this does is zone class misconfigurations by your parent, like a top-level domain, for example, you can now mitigate those as long as they were working at some point before the chain broke. And then also, if there's delegation class misconfigurations, like the example here, then you can mitigate both of those situations. And in fact, looking back at our survey data, we saw that about 28% of the events that we classified, or the instances of non-zero failure potential, would have been mitigated using this type of setup. Okay, so and the way we defined that was if the failure potential was of this, how do I say this? If the failure potential of the zone in question was less than the failure potential after applying its parent zones to it, then we consider that as something that would have been mitigated using this soft anchoring approach. Okay, so the way the soft anchoring works is basically it's very similar to RFC 5011, which is used for maintaining trust anchors. And your resolver is going out to your zones periodically and just re-authenticating those DNS keys that you have reserved as soft anchors in your repository to re-authenticate the chain of trust for those DNS keys. And the way that new anchors are added is every time a DNS key is added to the DNS key resource record set for a particular zone. So a new key shows up, then you're going to add that to your repository. And after it's been there for a particular amount of time to validate that it's actually valid. And then also if a new DNS key shows up with the corresponding DS record, then they look at that and say, okay, we'll add that into our repository. The way that they're removed is if the delegation is ever made insecure, meaning the DS records at some point in the line are pulled so that there's no path of trust to the bottom nodes, the zones below, I should say. Then the soft anchor is removed. Likewise, if the DNS key is revoked at some point, then it's removed as a soft anchor. Or if a DNS key and its DS resource record are removed, then that's how it's removed. So that's kind of the logistics behind how this works. Now, there are some limitations to this particular way of mitigating misconfiguration. First of all, soft anchoring doesn't help when the misconfiguration is at or below the zone, what I say, the bottom link in the chain of trust. So, for example, if there's a problem with edu, and right now Purdue.edu is not signed, then you can't use this approach with Purdue.edu, so Purdue.edu would still be broken. Okay. Also, you have to have this, I've mentioned this before, but you have to have a pre-existing notion of trust, meaning you have to, this DNS key that uses a soft anchor has to be pre-authenticated before you can use it. So the chain has to exist unbroken to the resolver before the break happens for this to work. And then scalability in terms of implementation. I'm not sure how feasible this would be if it's a lot of overhead for a resolver to maintain this or not. Okay, so DNSSEC visualization. One of the things that I do at Sandia is work on our production DNS services. And I was responsible for leading Sandia's deployment team, Sandia's DNSSEC deployment team. And we came across, so we signed our zones. I spent quite a bit of time looking at it and figuring out DNSSEC and trying to figure out the right way to do it. And we signed our zones, and then it wasn't until a few months later that we turned on validation of other people's zones. And the results were surprising. We were monitoring the errors as they came in and then trying to investigate what was going on so we could try and help other people with their DNSSEC setups. And what we were seeing was there were errors all over the map in terms of what was going wrong. And it was very difficult to troubleshoot because of the complexity of this. You know, if you saw a problem with Purdue.edu, was it in Purdue.edu, or was it in edu, or was it in the root zone? Those were some of the questions we had to ask. Was it only on some of the servers? Was it on all of the servers? So how would we troubleshoot this? So I came up with the idea to visualize some of this stuff, and came up with an idea which we now call DNS Viz, and it's available online at dnsviz.net. I'm going to show you some of the examples that we've seen using output from that. And I apologize, some of the images may not be as clear as I would like them to be because it's actual output from the program, but I'm going to show you a few of these. So here's an example. This is CERIAS.purdue.edu, and basically what you see, the blue nodes at the top represent the square at the top represents the root zone, which is signed, okay, and the blue represents that they are secure. Then the next rectangle you see below that is the .edu zone, and you see the chain. So you see you're forming this chain down below, okay? Well, the chain ends at edu with this NSEC record. Actually, in this case, it's an NSEC 3, but the point is that the NSEC 3 is used to say there is no DS record here, so everything for Purdue.edu is insecure, meaning it's just plain old DNS, okay? So that's why you don't see any more blue outlines below you. It's because it's plain DNS, because it's unsigned. So that's kind of the idea behind this, is if it's secure, you're going to get one of three results for the nodes, and the coloring will show you that. It's either going to be black for insecure, which is plain old DNS, light blue for secure or trusted, and then red would represent bogus, meaning there's some break in the chain somewhere. Okay, here's an example of a signed zone. This is penn.edu. They were one of the first EDUs to sign. And you can see a complete chain from their records there at the bottom. Now, if you go to the site, you can learn a little bit more about what some of the meaning of the different outlines and so forth. But really, I'm just using this to show you the colors and show you how secure versus insecure works. Okay, but you can see you can build a chain of trust from the bottom. So penn.edu, the SOA record is signed by a particular DNS key at the bottom. That DNS key is signed by another DNS key, so that's the start of your chain. That DNS key is mapped to by a hash in the .edu zone, and that hash DS record is signed by a key in the .edu zone, and so forth. Okay, up to your trust anchor, which is the top. So what happens when you have a break in the chain? Here's one example with fhtc.edu. This was actually taken today, So what happens is I color the signatures differently, purple if there's an expired signature. I don't remember when this one expired, but what it does is it breaks everything below it, and so now the nodes are colored red. So administrators can look at this and say, okay, I know where the break in the chain is, and the bogus nodes are below that. So I talked to you about, I mentioned an example with the top-level domain having problems. We actually had problems with a few. This one happened back in October. This was the .be top-level domain for Belgium. And their signatures expired for probably close to 24 hours, during which time validating resolvers were unable to resolve anything properly below .be. Okay? So when you get to the top-level domain area and you have problems like this. Now, granted, I'm not meaning to point fingers with this, but this is learning experience with everyone. Everyone's learning DNSSEC as we're doing this, okay? And notice something down at the bottom here is that it didn't matter that the signature on the .be, the SOA record, you can see that that one's colored blue, the one between the key and I'm looking at the very bottom left nodes. That one's colored blue, meaning the signature there was still valid, but the problem was the break in the chain had already happened further up with the signature of the other key. So the idea behind this was to find where exactly the break in the chain was and identify that, so that because if you were looking at just the RR-sig that covered the SOA record, everything would look okay. Okay. Here's an interesting one that we saw just last week. Again, another learning point. This was .kg, top-level domain. I believe it's Kyrgyzstan. And they had a problem where their signature wasn't yet valid. It was before the inception date. Normally, you would just wait for the inception date to come, and it would just work after that. Problem with this was it seemed to actually every time it was re-signed throughout the day, it would keep pushing the inception date back. So this was actually like this for about 2 days. We're not sure what the problem was that we were seeing there, but eventually it cleared itself up. And so, but during that time, again, validating resolvers were unable to validate anything below .kg. Okay. More learning experiences. This particular one is an example of where the DS record was changed, or excuse me, the DNS key, the role of the DNS key was changed. So you can see at the top of this, I'm going to say on the far right here, the Virginia.gov zone, you see that there's a DS record pointing to a particular key. The problem is that key needs to be self-signing, and you don't see a signature, a little edge going back to itself on that one, because that one no longer has a signing role. So what that is, it's a case of where that key used to be the primary key, basically, what they call a key signing key, and then they moved it to a published state. And because it's published only, it doesn't do any good for the DS record to point to that, and because you have to build this chain, and you can see that the chain of trust ends right there. There's no way for it to get down to the other records. And it also so happens that the signatures were expired anyway, so you had other problems. But that's an example of what the mismatch between DS record and DNS key looks like. It could have been the same also if there were no DNS key there at all that mapped to that DS record. Okay, Houston, we have a problem. This was nasa.gov just last week, where some of their servers were serving certain DNS keys, and other servers, some servers were serving the DNS keys and other servers were not. And that's the little exclamation point there. The warning symbol in the DNS key means that only some of the servers are serving that particular key, and also that some of the servers aren't serving signatures. So down here, this red one, you can't see it very well, but it's actually a dashed line, which is meant to represent that that some of the servers aren't serving the signatures like they should. So of course, the validating resolver that hits that is not going to have the signatures to validate it. This was an interesting problem that came up just last week with berkeley.edu, and it was actually a problem in software, the software version that they were running. And what it was is that, again, this NSEC record is important to prove to the resolver that it's an insecure delegation below, that the zone below is unsigned. So the signature, of course, of that NSEC record is also important so that it can be proven, so you can complete this chain. The problem is that a subset of the servers were serving an NSEC record with an invalid signature. So if you ever got that, then you weren't able to validate that the zone below it was insecure. Now in this case, you'll notice that these records at the bottom for cs.berkeley.edu are not red, they're actually black still, and that's because there is a valid path because some of the servers were serving valid signatures. Okay, that's the idea behind this, but it was actually an interesting problem that we came across. And then here's an example of another zone here. This is Honduras, and the second level domain com.hn, only some of the servers were returning the NSEC record, some were not. So again, if you hit those, you wouldn't get the proof that there was no DS record. And in this particular case, none of the servers were serving the NSEC record. So anything below this gov.my validators would not be able to prove that any of the insecure zones below that were actually unsigned. Okay, so you can see kind of the spectrum of problems that you look at when you're deploying DNSSEC. There are a lot of things that can go wrong, and you have to be very careful when you deploy it, as we found. Okay, so just as a summary, to summarize things here again, we rely on our DNS responses to be accurate and to be available as well. DNSSEC requires a lot of careful planning and maintenance. Soft anchoring is an approach that we have introduced to mitigate misconfiguration that we've seen out there. And a DNSSEC visualization at dnsviz.net is something that we've implemented to try and help administrators to troubleshoot and identify some of these problems out there. So I'm working on an internet draft to try and make this a little bit more formal, formalize this idea of soft anchoring, and also have some proposals in for improvement of this DNS visualization tool to include monitoring and alerts that go along. So some of this work was done in collaboration with Intel and UC Davis, and these are the folks here that I'd like to acknowledge. So are there any questions? Yeah.
So with your soft anchoring, is there a method of revoking keys? Is that implemented?
Yeah, good question. So there is a method for revoking, and that actually follows from, I'm going to go back here. So, so it follows from RFC 5011, which is used for trust anchors. And RFC 5011 introduced what's called the revoke bit in the DNS key resource record set. So if you see the revoke bit set, then you know that's a revoked key, and that way a validating resolver that has that configured as a trust anchor knows that it can throw it away. Otherwise, it won't throw away something. And so I've adopted that into the soft anchoring approach, which mimics that RFC 5011 in a lot of ways. Yeah, good question. Other questions? So you guys all going to go home and try out DNSSEC now? Yeah, it's a lot of things to look at. So, and it's an interesting research area because it's so new. And I don't know if you guys were aware, but this was one of the things that the U.S. government had actually issued a mandate to deploy to all the subdomains of .gov just 2 years ago. And it's something that a lot of the .gov sites are still working on. And it is, I mean, as you can see, there's a lot of room for growth here. And I don't think, I do think it's an important issue, and it's something that needs to be addressed to how to make this work. But as you can see, it's a lot of learning.
Any other questions?
I'll ask another.
Yeah, sure.
So do you have any idea of some sort of timeline by when we should expect most sites to be signed? Do you think that will happen?
So that's a great question, and in fact, very timely, because some of it depends on your parent zone. Okay, so if you're a .com, for example, then it's easiest if your parent zone .com is signed. Well, it turns out .com introduced their DNS keys just a day or two ago, and they'll finish their transition in probably about a week or so, I believe, fairly soon anyway. And so that means .coms will start being able to be signed. Now, in terms of, I'm not sure I've answered your question in terms of timeline. A lot of the EDUs are starting to do it, and I think it's going to be hard. My personal opinion is it's going to be hard for a lot of the money-making folks on the commercial side to do it, because they may not see, until there's a particular DNS breach that they'll say, well, it's going to cost us too much money. And as you can see, even a little bit of downtime for somebody who gets a lot of traffic, costs them a lot of money in terms of their customers. And so I think there's going to be I think it's going to be slow adoption rate on the commercial side, personally. Until there's a problem, then everyone will jump to it, right? So. Yeah. Thank you. Thanks for having me.